Well, thank you. I apologize for the appalling title of my presentation. It sounds horribly technical. So I'm going to be talking about high contrast imaging. So we'll talk about trying to directly detect extrasolar planets. I'm going to try to do two things here. First, I'm going to try and show you how we do this today. And I'm going to tell you the things we start to implement to do it better than we currently do. And I'm going to teach you how to whisper to speckles. And we'll go how that goes. Now,
OCA stands for?
Observatoire de la Côte d'Azur, which is where I'm from. Thanks to the wonderful introduction to the detection techniques of extrasolar planets you had this morning, you've seen this picture a couple of times. And so again, we look at the population of detected extrasolar planets to the day, a couple of months ago maybe, for this particular picture, where we look at the way planets distribute in terms of semi-major axis to mass, and with a color coding here that shows the way those planets span in terms of age. Now, you've also seen that there's a wide variety of techniques that are used to detect those extrasolar planets, and not all of them do probe the same parameter space. We've talked about the Hodge-Peter standing around here, all of the Kepler planets laying here, going toward the low mass, very close to stars, and all of the direct imaging planets that have been detected in the upper end of that diagram here, at large angular separations, orbital separations for the most part, and fairly high mass objects. And you notice also the color, we are mostly looking at very young objects. Those planets are somewhat easier to detect because they're still cooling down, and we're looking at their infrared signature, which is easier to detect. We've heard many times that detecting extrasolar planets is very hard. You have to keep in mind that the playground is actually very big, and it's exploring, it's a multidimensional parameter space that we're going to look at. And we've talked earlier about things like polarization, we've talked about things like spectroscopy, we've talked about things like time series, and here we're mostly going to focus on the spatial separation of the planets from their host star. The difficulty with, regardless of these techniques, is that you have very bright star, which can be noisy by itself, surrounded by faint objects, and we're trying to beat the photon noise of that planet, of that star, and to see the faint signature by exploring in a clever way this 5-dimensional parameter space, usually by improving the resolution along one of these axes. And so we're going to try to improve the resolution along the spatial coordinates of the parameter space to help us. When you heard it, it's really hard because even if you take the textbook description of what a telescope is, you know, this classical diffraction pattern for the Airy function for which you draw a radial profile, which, you know, as you go further away from your object, gets fainter and fainter and fainter. If you try to place the objects we're trying to target, extrasolar planets, in that diagram, well, the brightest of these planets I'm talking about, they lay somewhere right here. And if you look at things like Earth-like planets, they lay at the very bottom. So you have many orders of magnitude to beat in order to directly get access to the light of these objects here. That tells you how difficult that thing is. But by using techniques, I mean, we're getting close to that. One of the take-home message of this is that telescopes are terrible to do this, because telescopes were originally designed to collect as much light as possible to image faint stuff, and not at all designed to produce high contrast images of faint stuff right next to the very bright stars. So this is our starting point, and we're trying to tweak things in order to help us get closer to that state where we can do high contrast imaging. So the reason why we have this funky little ring surrounding this image here is because the telescope, even perfect as it is, features a sharp edge, and the sharp edge is responsible for these high spatial frequency structures that extend very, very far out and dominate the field no matter what we are doing. Now, there are some very minor things you can do to dramatically change things, including taking a piece of cardboard, cutting something to the right shape, applying to your primary mirror, and do something like that. Now, suddenly, because you've well chosen the shape you want to give to this thing, you were able to create naturally, without doing any additional magic, high contrast region in your images where the luminosity suddenly drops by several orders of magnitude, right? And if you compare the two things, you clearly see by the magic of a piece of cardboard, you were already able to bring things down by 2 orders of magnitude, much closer to the goal you already are.
So that will only be in the triangles to the right and left.
That's right. So then if you want to care for something that would be that way, or you would either have to rotate your mouse or wait for the things to move in the sweet zone. Yeah. That is the roughest way of doing things. There are clever tricks you can play to achieve the same goal in a more efficient manner, because it comes also with some drawbacks, like the fact, as you notice here, that this first zero dark ring here ends up being much farther away. So essentially, you're losing spatial resolution along that direction. But you know, there are clever things you can do to get around this. And this was a picture for the perfect circular telescope. Real telescopes are even worse than that because they feature things like central obstruction, where you have to put a secondary mirror. And typically that thing has to be held by something. And so we have struts that hold it. And that aperture diffracts like you don't want to see it. And so you have to play some very clever things to try and do things like remap using complicated optics that violate a lot of the principles of imaging optics in general, to go from an aperture that looks like this, which is terrible for high contrast imaging, to something that's going to look like this, which is very nice because the diffraction pattern of an aperture that would be shaped like this is essentially ideal for high contrast imaging.
To the SRP and
those are like so this is something that we call this spider removal plate, and like 4 pieces of glass that were able to somehow erase the signature of the spiders, the things that hold the primary mirror, the secondary mirror. And this other device here is a phase-induced amplitude apodization, which redistribute the light from something that would look like this in the input, and remaps it in a way that does this that way. The clever thing about this is that you are not losing any light. You're actually not putting a piece of cardboard anywhere on your aperture, but it makes the imaging properties of the system very complicated. So that's how you sort of address the rough features of diffraction of your aperture. Now the question comes is, you still have a very bright, you still have a very strong spotlight in your image, and you want to see the faint firefly standing next to it. And what you want to do is something that essentially replicates during a solar eclipse, right? By the magic of optics here, somehow cleverly superposing something to the image of a bright star, you can reveal those very fine structures that were present all the time that was just invisible in the first place. Now, how do we make an eclipse in a box? That is the secret of this magic thing called the chronograph. I'm going to explain to you how a chronograph operates. A chronograph, you have to picture the light collected by the telescope coming this way, is made of 2 or 3 parts. I'm going to say 3 parts to be thorough here. There's 3 important places in a chronograph that are going to play a part to help you do high contrast imaging. The first part, we talked about it. This is what you can do to your aperture in order to make it more friendly for high contrast imaging. phase called apodization, meaning the stuff that's going to cut the peak of the PSA, of apodizement. There's a second place here, which is the most intuitive of the places. I'm blinded by the projector. I'm just going to put my thumb and hide it from my eye. And that works to some extent, but if you do that, and that's the way this chronograph was invented, you realize that a lot of light gets diffracted anyways and filters through here. So you have to go to a third place, which is conjugated with that place. So you're looking at a pupil again of your telescope, and you're putting an additional mask called the Leo stop that's going to clean the diffracted light. So since this is cool, I have to tell you a little bit technically how this works. There's a couple important things that to keep in mind, which make your life easy. The first one is that since you're going from pupil to focal planes, the far field diffraction applies, and so you don't have to worry about complicated Fresnel diffraction things. It's the Fourier theory that describes the way the complex amplitude propagates through your system. So the computations end up being very simple. And your system, you have to keep in mind that your system, your optics here, are going to interact with the electric field of the light. And in the end, your camera is going to record an image, which is an intensity pattern and not something that's the electric field. And of course, because anything that's not exactly on axis, a planet, the light of that planet is not going to go through that little mask here. And so it's not going to be affected by the function of the chronograph, mostly. So we look at those different points here. This is the image from the telescope. If you don't know anything about it, and so you essentially see nothing but the diffraction produced by the aperture. We're not doing any apodization here, just to see better the functions of the system. So this is what you need to do if you have just to put your thumb in front of the light source. So you essentially just hide the bright part of your image here, but it's pretty clear now that you have lights that still makes it through. That's diffracted because the aperture is not far from ideal. But if you go back to this plane here, you can see that the intensity left over from this system is not randomly uniformly distributed, but is located around specific areas that you can simply further mask out with a mask that looks very much like the original aperture, but just a little fatter, and you're left with not much of the light to start with. That is the concept of the Leo chronograph. If you put an apodizing plate here, you get the apodized Leo chronograph. You get all of the flavors of these chronographs. The interesting feature is that, of course, if you are looking at something that's off axis, it misses the focal plane mask, and so the light must really make it through here, and that mask just takes a little bit away of that light, so you don't have a full 100% throughput, and you have, for an optimal design, something like around 70% off axis. I have to provide you with the means of reproducing what I just showed you here. And so here I suppose you will have access to those presentation slides anyways. And so you have the way you can parameterize the system using a specific set of coordinates for what's happening in the pupil, what's happening in the image, and what's happening in the Leo plane. And a couple of functions that are going to describe the apodization, the aperture profile I want to put in, something that describes the focal plane mask, something that describes this Leo stop, and be okay with using the Fourier transform. So if you use these equations, I'm not going to go through them. Here you have an algorithm that is going to describe you exactly the way and produce images of the focal system of this chronograph. So very entertaining, and you will quickly discover, you can fall into the trap of trying to discover the ideal chronographic system. Many have fallen for that one. It turns out that there's plenty of optimal solutions, including some of the ones I've talked about. And it's very easy to get carried away. I almost fell down that rabbit hole also myself. But one take-home message that I want to leave you with is that all of these designs, regardless of how clever and how efficient they are, they all share a fundamental weakness which we're going to look at. The way I've described the chronograph, it's a system that is designed to suppress the static diffraction introduced by an optical system. The telescope, the transfer optics, and the instrument itself. The higher performance of that chronograph, that is, the higher the contrast it can produce and the closer you can get to the star, the more sensitive it's going to be to tiny changes in operating conditions. And so from the ground, chronographs in practice are in real trouble because nothing ever looks like that. In practice, when you're looking from the ground, if you don't do anything about it, your ideal diffraction pattern essentially looks something like that. And so you have images what I'll describe from going from diffraction dominated, telescope diffraction dominated, or diffraction to images that are dominated by the seeing of your telescope. So good luck trying to just mask out the light from the star in there and leaving the light of faint sources in the neighborhood untouched. So I have to tell you, there are measures you can use, which are tools like adaptive optics. The way an adaptive optics system operates is we acknowledge the fact that the atmosphere messes up with our image and that those errors are going to propagate through our system and affect our science camera images. The adaptive optics system relies on a funky little unit called a waveform sensor that is able to sense exactly what's happening, feedback an active piece of optics that helps improve the image quality. And you go from something that would look like that to something that looks like this. And the exact morphology of what that image is going to look like is going to depend on the specifics of the instrument. You may have seen images produced by the Sphere high contrast imager, for example. Have you ever wondered why there is a bright ring around those Sphere images? I'm going to tell you why.
There's no Leo stop.
No, there is a Leo stop. This is the secret here. Going back to the aperture of the telescope, you can think of the aberrations introduced by the atmosphere as a series of oscillations going over your aperture that are going to diffract light. And when you have an oscillation across your aperture that introduces a certain number of cycles, it's going to produce a pair of speckles, the ones we're going to list on in a minute, which are, the faster this oscillation is across the pupil, the further away the speckles are going. If you try to introduce those oscillations yourself, your deformable mirror only gives you a certain number of actuators, and beyond, so in this case, it's about 50 actuators across the pupil. That means that the fastest spectral frequency you can generate is going to be 25 cycles across the aperture, which is going to place or correct the speckles no further than 25 speckles away. And this is exactly what you see here, where the adaptive optics does a wonderful job until a cutoff frequency beyond which you can't do anything.
1 billion more accurate.
Yeah, there's a question of money. It's always is, right? But that was the rationale from going to a classical adaptive optics system to extreme adaptive optics system. It's the same thing, except with more actuators to get that. And so I showed you all of this already. Now, this is an interesting thing to look into. If you were to describe the complex amplitude of something with that oscillation across the aperture, you have a complex amplitude, which is going to be the sinus is here is how fast that oscillation is going across the pupil, and it's of course characterized by an amplitude which you can adjust. If you go in a small angle approximation, you can linearize this form here, and you get an expression for this complex amplitude, which looks like this. The job of the chronograph is to erase that part. So whatever the atmosphere is going to add to your system, despite the adaptive optics correction, is going to be to filter out and manifest itself in the form of speckles, whose properties are going to depend on how fast those modulations happen on the aperture. What you can do with this very simple model here is look at what the contrast of the corresponding speckle is for a given amplitude of that modulation. And because the intensity is just the square of that complex amplitude, this is what the expression of the contrast is, 2 pi times that amplitude divided by lambda, all of it squared. So now let's do a requirement. Let's say we want to build a system that is able to directly detect soft luminous planets. What that means is I want a system where the contrast is at least better than 10 to the minus 6. Now, what does that mean as to how stable my correction should be in terms of amplitude on the correction of the waveform, right? Well, you just invert that relation here and get something that's proportional to the square root of the contrast divided by 2 pi. So 10 to the minus 6 for 10 to the minus 3, divided by 2 pi, you end up essentially with certain nanometric requirements on the quality of the wave. The best adaptive optics system of today are about 2 orders of magnitude worse than this, which is sort of why we currently can't do much better than the self-luminous giant planets, only after a lot of post-processing. And there's a couple of the things that make things complicated. I drew this idealized picture of what adaptive optics system does, but you have to keep in mind that there's a lot of optics that are not part of the optical path toward the adaptive optics system that the waveform sensor just doesn't see. And so the adaptive optics may try to flatten the waveform as best as it can. It may not necessarily flatten it as best as it can for the science camera. And in practice, we do see this in data produced by ground-based telescopes. We see static aberrations in the system surviving over time scales of several hours that the adaptive optics system is just oblivious. And in the absence of a better solution, we are left with post-processing, which is really the major piece in that game. And then to add to this, I want to point out, and I'm going to show you this by respinning to speckles a little bit, the fact that a chronograph or high contrast imaging instrument may not necessarily be happiest when the waveform is flat. So what you do when you're affected by that type of biases, well, you do what every practical astronomer does, you try to calibrate those errors. And so this is a simulation of an image produced by a telescope where there is a faint companion hidden in there. What you do is you take a second image after rolling the telescope 180 degrees and find the companion. They're invisible in those two things, but if you do what's forbidden, which is the difference between two large numbers, you actually can find your companion, and this is the basis of the technique called angular differential imaging.
So where is it from?
In both places here.
Both places.
Yeah, it's been subtracted. You know, it's probably here in the first image, and it's probably here in the second image. So you end up with that planet twice. And this is the big player in current direct imaging campaigns from the ground. This is what works. Other options, of course, include things like doing the same thing with two images of two different polarizations, or two images in two different spectral bands, or two images with two different modulations with coherence. I'll talk about this. In practice, this is what you get if you look at a raw image produced by one of those large telescopes. This is a super telescope, and you have something. This is a Kappa Andromeda B, like a high mass, probably close to 30 Jupiter mass companion around this bright star here. This is what the raw image actually looks like And this is what the post-processing gets you. So we, in order to find the faint planets around things like HR 8799, something you really need post-processing to actually operate, because most of the time they're just invisible. So now try to introduce this idea of changing from an operating mode where you just have a one-way conversation with the light from the star that's just coming to your camera. You require sufficient data, you go back home and you try to post-process it and turn this into a dialogue where you're actually going to try and speak to the speckles present in the image to do something about it. What I suggest you do is to actually try and figure out whether something present in your image is coherent or not coherent with the light of the star. So you take whatever structure in your image you want to characterize and you ask yourself, well, is it a coherent structure or not? If it is, then I'm going to tell you how you do that. Then that means that the light belongs to the star and it is subtracted from the system optically. If it's not coherent, well, congratulations, you discovered something around this bright star. And what do you do to suppress a speckle, if it happens to be a coherent structure here? Well, a speckle is characterized by two things, an amplitude and a phase. It's a complex amplitude. What you have to do is find out that amplitude and the phase, and just like and add a modulation like this, which is going to cancel out one of these structures. And you repeat that until your image is clean of other residue. So you predefine a region over which you're going to try and do spectral control. You pick whatever bright structure, which is going to be this one, for instance, and you measure its intensity and its position in your image. You convert that position into a spatial frequency. You know how many lambdas over these it is away from your central star, so you know what spatial frequency it corresponds to. And because you've measured its intensity, you don't have access to its phase. You only have access to an estimate of its amplitude. With your deformable mirror, you can add a modulation like this with the spatial frequency that is going to correspond to that structure. And you're going to look at the way that light interferes with whatever you've added in place. So you have a classical interference equation here of two terms. The thing you'd like to find and the thing you've added, for which you know everything. And you want to be able to conclude, well, is it coherent or not? Is it a speckle or not? And this is the kind of thing that you can do. This is the intensity that you would record on a given speckle if you were to do nothing about it. And this is what you do when what you record when you measuring that intensity, decide to add a probe of identical amplitude and you modulate the phase. What that means is that spatial frequency, you're just going to slide it across your aperture and just one cycle suffices. And what you're going to look at is the way this interference pattern works. And you're going to find that that curves go to a minimum, which is what you have to do to erase that speckle from the And this is something that is beginning to operate on sky, where you can, get from something like this to something like that. So before post-processing, you were able to reduce the contrast in your image by an order of magnitude. And of course, while I describe the thing one speckle at a time, you can multiplex things and do it for the whole field simultaneously. With the hope of being able to achieve things like this, which is the kind of thing we can do when we're working in the lab under stable conditions, here you have to remember that, like I said, the adaptive optics is not doing a perfect job, and there's a lot of things that are still being improved. When you're doing this in the lab or when you're simulating space-like observing conditions, you can go very, very deep using this kind of things. So I'll finish with that. And remind you what we started with here, that we have plenty of hard planets to look at, and you've heard me talking about separating them in terms of spatial coordinates. You've heard other people talk about using polarization to discriminate things. You've heard about using time and series. And probably the best way to address this is somehow to explore multiple dimensions at the same time. And benefiting simultaneously from high spatial resolution with high spectral resolution, or high spatial resolution and very good time resolution, for example, during a transit, might be the ways to actually really push all of these types of techniques. Well, okay.